Hello, this is Todd Frazee, and welcome to ADVM 12. This is the first lecture covering the content of Chapter 1 in Unit 1 of the course. Not all of our units will be on one chapter after another, but most of them are. The larger chapter, I'll split into two units. So this is Introduction to Dimensioning and Tolerancing, and since this class does have a prerequisite, you're likely to have already know a lot of this content, but it's review, and it's a tremendous amount of terminology and memorization of symbols and processes in this class, so it's good to have a baseline and that we're using standard language. Okay, so here we go. We've got our introduction. In this lesson, you will discover why specifying dimensions and tolerances according to an established standard is essential for clear and accurate designs. You will learn about the history and development of dimensioning and tolerancing methods and explore the roles of key members who can assist in the design process. You will also learn how to interpret and create 2D orthographic views using orthographic projection and understand the types of documentation included in a product definition data set. Finally, you'll examine how changes in the industry could impact dimensioning and tolerancing practices. Okay, our objectives in this lecture or lesson is to explain the importance of specifying dimensions and tolerances in compliance with applicable standards, to recall the history and development of dimensioning and tolerancing methods, and explain how teamwork can result in better definition of dimensions and tolerances in the design process, and to recall the job titles of those who can assist on the design process team. We're also going to recall the dimensioning and tolerancing skills needed for success in design or production-related occupations. We're going to identify and explain the types of documentation, including a product definition data set. We're going to understand the relationship between 2D orthographic views and how they are created using orthographic projection, and explain some possible industrial changes and the impacts of these changes on dimensioning and tolerancing. Standards provide needed clarity. Tolerances are the acceptable dimensional variations permitted on a feature. So how much can that feature vary and for the design to work as intended? Tolerances enable achieving the best product at the lowest cost. Tolerances must be correctly calculated and applied and interpreted. And correctly applied tolerances result in fabrication of the intended design. The results of incorrect tolerances. Excessively small tolerances can increase fabrication costs, which limits the number of potential suppliers, increase fabrication time, and excessively large tolerances can increase assembly cost. Parts may not fit in the assembly, and assembly function is negatively impacted, which can cause customer dissatisfaction, results in increased returns. Technological developments in product documentation have occurred over time. The establishment of distance measurement standards, and there are two used in the United States. There is the U.S. customary system, which uses the inch, and we are one of 4 countries in the world that have our own unit system, rather than using the SI system, which is the metric system, which uses the meter as its basic unit. The establishment of dimensioning and tolerancing standards and the emergence of computers and computer-aided design, or CAD. Drawing note for unit measurement is required. So the unit measurement has no effect on the dimensional application. So whether it's metric or inch, the physical size of the product is the same. It's just expressed in a different measurement unit. It doesn't affect the numerical values shown in the dimensions and how dimensional values are shown. And dimensions are expressed in either inches or millimeters. And note in the product definition to prevent confusion. And so the current version of the standard suggests that it should say all dimensions are an inch or explicitly say all dimensions are a millimeter. Now, the previous standard was that unless otherwise specified, everything's an inch. And so on older drawings, you're going to have the assumption it's an inch unless it says millimeters on it. Okay, the development of distance measurement standard started with things like cubits, spans, palms, and digits. They've been in use for about 5,000 years. There's a bunch of other ones: stones, hogsheads, rods, hectares. But they're based on defining features present in nature. The royal cubit used by the Egyptians was made of a black granite block based on the pharaoh's arm, and the reference against which the measuring sticks were calibrated. Granite actually is a good choice. It's nice and stable. We still use it for modern inspection, but I believe every time the pharaoh changed, the length of the anatomy was slightly different, so then your system keeps changing. The standard meter development was probably the biggest achievement to get away from that type of definition, as our foot and our inch were originally defined off the length of the king's foot, and I believe the division of it by 12, which also works out about typically the distance between the knuckles on one of your fingers proportionally. But the meter standard was developed in 1799, and they used 1/10,000,000th of the distance from the North Pole to the equator when measured along a longitudinal line passing through Paris, France, because it was invented in France. And it spread through most of Europe in the early 1800s because Napoleon cleared through Europe in the early 1800s and established the metric standard throughout Europe. The standard meter changed, or at least how they define it. It was still pretty close to the same size, but we're getting better and better technology, and it's defined by the distance equal to this really big number on the screen there, wavelengths in a vacuum of radiation emitted by a specific form of krypton. So much more accurate. And then the standard meter in 1977, there were advances, and it's defined by the distance traveled by light in a vacuum during some really, really small fraction of a second. So our ability to measure increased in accuracy dramatically, going from 1799 to 1960, and then even another fold of accuracy from 1960 to 1977. This also allowed measurement tools to increase in accuracy. Before the metric system or decimal system, you'd be using that scale there and outside or inside calipers to measure things. You're transferring the numbers. You're lucky to get plus or minus 30 thousandths or a 32nd of an inch using that method. And then on the right, we've got a dial caliper that works in decimal inch. You can easily measure within thousandths of an inch or 0.005 of an inch with that device. And there's a whole slew of devices that are much more accurate that have been developed. The development of documentation standards. Back in the old days, they would actually build to a model, and then example is this wooden yoke. It was built to a crude distance standards, to which tolerances would not be logical. So it just had to be within the width of a couple of animals are going to go through that yoke, but they didn't follow a consistent system on what a palm or a span or a cubit. Technical drawings, didn't actually come into of orthographic projection did not come into being until much later when they were designing the Spanish Armada. And so up until that point, it was models. Everything was made to models, physical models. Okay, so the dimensioning and tolerancing standards developed and maintained currently in the U.S. is the American Society of Mechanical Engineers, or ASME. Tolerances smaller than accuracy of distance measurements standard are not appropriate, and accurate distance measurements standard essential to specify and achieve accurate dimensional results is what they control. So they're not going to govern measures of things that are other than distance. Okay, dimensioning and tolerancing standards. The standards provide terminology, symbols, and methods to define and communicate tolerances. They allow for a single interpretation of requirements, and applicable standards must be known. When product definition is based on a previous standard, that standard must be used to determine applicable requirements. So if you have old drawings, they're held to whatever standard is written on that drawing until they're revised. So there have been some changes recently where they drop some symbols that we'll talk about later in the class. We'll still learn about them because you're going to see those symbols on legacy drawings and need to know how to interpret them. Okay, tolerances, machine quality, among other factors, affect feature variation. Tolerances are essential to define the amount of acceptable variation. Tolerances specify acceptable dimensional variations permitted on a feature and should only specify the degree of dimensional accuracy needed for parts to assemble and function properly. This has actually been a problem more recently. You're making expensive products to a much tighter tolerance than is really required because the machines can do it. Okay, applicable dimensioning standards. So this class is on ASME Y14.5. Dimensioning and tolerancing is where the standards are defined. There are also a whole slew of other standards. For example, ASME Y14.8 is for casting, forgings, and molded parts. ASME Y14.41 is for digital product definition data practices. ASME Y14.46 is product definition for additive manufacturing. And ASME AED-1 is an aerospace and advanced engineering drawing standard. So there's tons and tons of standards. This is just a few of them. Okay, standards-based tolerancing. Geometric dimensioning and tolerancing provides a means to specify complete control of product variation. Supports application on solid models and on orthographic views. It's sometimes called position tolerancing. And GD&T is a general term used for tolerances applied to part features. Okay, the evolution of ASME Y14.5 dimensioning standard. All started right after the Second World War. And the first version was Mill Standard 8A in 1953. And on the right here, we have the most popular car sold that year, which was the 1953 Chevrolet Bel Air. Okay. And to give some context, we had a revision in 1959, and the most popular sold car that year was the 1959 Chevrolet Bel Air. Okay. Look at that, I found another red Chevrolet. In 1963, the standard was revised again. It was Mill Standard 8C. And we have a 1963 Chevy Impala there. Fast forward to 1966, the military got sick of maintaining standards, so they started spinning them out. And a federal agency, for a short time, controlled the standard, which is the USASI. And it's when the designation Y14.5 was adopted in 1966, and we have the fastest. We basically have the most popular car sold that year was the 1966 Ford Mustang. Now the standard stayed the same for a bit, and then it shifted over to a private company called ANSI, or American National Standards Institute. Kept the same numbering system. It's Y14.5-1973. And when I got halfway through doing my research here on CarOrigins.com, I didn't realize that at some point they were going to switch from automobiles to the most sold family of cars. So in 1973, more F-Series pickup trucks were sold than anything else, but that included multiple models. I did find a red 1973 F100, I believe that is, or F150. And then we move on to the next standards. We've got ANSI Y14.5M in 1982. I'm not sure what happened. That was the most sold car, but it's the Chevrolet Celebrity. I couldn't find a red one, and I couldn't find a image of a restored one, so I'm not so sure that car is still as popular as it was back in 1982. Moving on, it evolved again with the standard changing in 1994, when again the Ford F-Series pickup truck was king and #1 in sales in the US. Then it was revised again in 2009, and again the Ford F-Series pickup truck. I probably should redo this the next time I do this presentation and go with the most popular sedan sold, because I think this statistics are stacked here with doing a whole series of models. Okay, and our last one is the ASME Y14.5, and again the F-Series Ford truck. It was the most popular. More of them were sold than any other vehicle in 2018. Okay, so we went from Chevy in the early days to Ford. All right. That's just kind of an indication of, you can see the progression of evolution of technology along with the standards. Okay, the reasons for new standards. One is to keep current with industry standards, new methods of dimensioning and tolerancing, to add new and expanding existing capabilities, to meet emerging industry needs, like additive manufacturing was added as a standard in entirety, clarify current methods, and to support product definition practices such as applications on solid models, which is still kind of in its infancy, and to remove obsolete methods of definition.